Here's a scenario that breaks synchronous communication. Your payment service needs to notify 5 other services when a payment completes. The order service updates order status, the inventory service decrements stock, the notification service sends a confirmation email, the analytics service records the transaction, and the loyalty points service awards points. If you do this synchronously, the payment service calls each of the 5 services in turn, waiting for each response. You have several problems. The payment service is now coupled to all 5 services. If any one of them is slow, the payment request is slow. If any one of them is down, the payment fails. Adding a 6th service means changing the payment service code. Asynchronous messaging decouples the payment service from all 5 consumers. The payment service publishes a single event, payment completed. Here are the details. It doesn't know or care who consumes that event. Each consumer service processes the event independently, at its own pace, without blocking or coupling the payment service. This is the fundamental motivation for messaging systems, decoupling producers of information from consumers of information in space. They don't need to know each other's addresses, time, the producer doesn't wait for the consumer, and availability. If the consumer is down, the message queues until it comes back. The book distinguishes 3 types of messages, and getting these right shapes your entire system design. Command messages tell another system to do something, process this payment. Event messages notify that something has happened, payment was processed. Document messages transfer data. Here is the customer record. Command implies responsibility, the target must act. Events are notifications, the source doesn't dictate what happens next. Documents are raw data transfers with no implied action. Confusing these leads to tightly coupled systems masquerading as loosely coupled ones. Before you can understand pub/sub, pipelines, and task distribution, you need a solid mental model of what message queues and streams are and why they're different from direct function calls. A message queue is a buffer between a producer and a consumer. The producer puts messages into the queue and moves on immediately. It doesn't wait for the consumer to process the message. The consumer reads from the queue when it's ready and processes messages at its own pace. The queue holds messages until the consumer picks them up. Think of it like a postal mailbox. You drop a letter in the box, you're done. The postal worker comes by when they come by, picks up the letter, and delivers it. You don't stand there waiting. The mailbox is the queue. The backpressure mechanism that queues provide is one of their most valuable properties. If your consumer is processing 1 message per second but your producer is publishing 10 messages per second, the queue fills up. This is a signal, a backpressure signal, that your consumer can't keep up. You can respond by scaling consumers, throttling the producer, or shedding load with explicit policies. Without a queue, the fast producer simply overwhelms the slow consumer. The distinction between peer-to-peer messaging and broker-based messaging is fundamental. In peer-to-peer messaging, systems communicate directly. Service A opens a socket connection to Service B and sends data. 0MQ is the canonical tool for this. It's extremely fast, messaging overhead is in the microseconds, and there's no central broker that can fail. The trade-off: each system must know the addresses of the systems it talks to. Broker-based messaging adds a central intermediary. RabbitMQ, Kafka, Redis pub/sub. Producers send to the broker. Consumers receive from the broker. Neither needs to know about the other. The broker adds reliability features, message persistence, delivery guarantees, retry logic. The trade-off: the broker is an additional component you must operate and keep highly available. When you pick a messaging system, one of the most important questions to ask is, what does it guarantee about message delivery? The answer has deep implications for how you design your consumers. At most, once delivery means a message is delivered 0 or 1 times. If the delivery fails, the message is not retried. The consumer might never see it. This sounds alarming, but it's appropriate for scenarios where occasionally missing a message is acceptable: real-time metrics, telemetry data where gaps are fine, low-priority notifications. The advantage is simplicity and performance, no need to track which messages have been delivered. At least once delivery means a message is delivered 1 or more times. If the consumer acknowledges receipt and the acknowledgement is lost, the broker retries. The consumer might process the same message twice. This is the most common guarantee in production messaging systems. RabbitMQ's default configuration provides at least once delivery. The design implication: your consumers must be idempotent. Processing the same message twice must produce the same result as processing it once. A consumer that charges a credit card cannot process the same message twice. Exactly once delivery is the holy grail: every message delivered precisely once, no duplicates, no losses. It's also extremely difficult to implement correctly in a distributed system and comes with significant performance overhead. Kafka's transactions feature provides exactly once semantics within the Kafka ecosystem, but guaranteeing exactly once across your entire system boundary requires careful coordination. The practical recommendation from the book, designed for at least once delivery with idempotent consumers. This is achievable, well understood, and provided by standard messaging infrastructure. Build idempotency by tracking which message IDs you've already processed, or by making your operations naturally idempotent. Writing the same database row twice produces the same state as writing it once. The architectural choice between peer-to-peer messaging and broker-based messaging is worth dwelling on, because the wrong choice for your context creates problems that are hard to fix without a major refactor. Peer-to-peer messaging, using a tool like ZeroMQ, is the right choice when you need extremely low latency, want to avoid an additional infrastructure dependency, and have a relatively small number of well-known communication partners. ZeroMQ is a C library with Node.js bindings. Latency is in the microseconds. You get sophisticated socket patterns, push/pull for work distribution, PUB/SUB for broadcast, REQ/REP for request reply without any broker process. A ZeroMQ-based system can process millions of messages per second on a single machine. But the limitations are real. There's no built-in message persistence. If a consumer is down when a message is sent, that message is lost. There's no built-in retry. The routing topology is embedded in the application code, which means changing communication patterns requires code changes. Discovery is manual, you need to know the address of every peer. Broker-based messaging, using RabbitMQ or Kafka, is the right choice when you need persistence, guaranteed delivery, complex routing logic, and loose coupling between producers and consumers. RabbitMQ is the Swiss Army knife, flexible routing with exchanges and queues, easy to set up, great tooling, used by Instagram, Reddit, and many other large platforms. Kafka is optimized for high-throughput event streaming with long-term event retention, used for event sourcing, stream processing, and audit logs where you need to replay historical events. The architecture of your messaging system, peer-to-peer or broker, which delivery guarantee, is not a detail you can easily change later. It shapes how your services are written and how your system behaves under failure. Make this choice deliberately.